Hello students, today's class is about potential due to a point charge. So, we have read about the force in electric field, then we read about the electric field itself, then we read about the potential energy due to the electric field, then we defined the work done and storage of potential energy with respect to work done. In the previous class we have learned about the potential, and now we will read about the potential due to a point charge. The system is same here also. See the diagram to understand it very clearly and listen to me very carefully. We are having our charge capital Q here. Our charge capital Q here, which is a positive charge. Which is a positive charge. At infinity, we have our test charge, test unit charge. Test unit charge. Need to define what is a test unit charge? Within a minute I will come to this. First we will read about the diagram. Test unit charge, which is at infinity. This unit charge is also positive in nature. Now we did external work. We did work on the test unit charge by providing force external. By providing force external, what we did? We did work. Work is done by system or by us. So we provided force external and we did work on this test unit positive charge, and we brought it to a point P dash. We brought it to a point P dash. We need to bring this charge to point P, but we are taking one intermediate position which is del R distance away, so that we can define it properly for a given small distance. For a given small distance. Okay. Now from P dash to this some unknown number, the distance is del R dash. Del R dash. What is the distance from our charge Q to P? That is R. R vector. This is R. Okay, this is R. This is the distance. So first we will try to define everything with respect to del R dash. Del R dash. Then we will define it for this system. Okay, from P to the Q. Okay, this is the diagram. This is how we are trying to find the potential to the point charge, and the point charge is present at infinity. That is a test charge which is also positive in nature. So test unit charge is a charge which is used for testing. First thing, this test charge is negligible. Hence, it is just used for testing the electric fields, the potential, the energy, the work done, everything. And then unit charge implies a charge of 1 unit magnitude. 1 unit magnitude. This charge can have unit of 1 coulomb, 1 microcoulomb, 1 millicoulomb, or anything. So this charge is having everything in unity, in 1, not more than 1. Everything is in unity. Hence it is called unit test charge or test unit charge. And why we are taking it unit? Why not 1 coulomb charge? Because we are not defining this charge with respect to the coulomb, microcoulomb or millicoulomb, but we are defining for any given unit of the charge, but that unit should be 1. That unit should be unity. And here the other unit signifies it is unity 1. That's all. So that's why this is test unit charge. Now we'll come to our concepts over here. Consider a point charge capital Q at origin. This position is origin. I have already explained in the previous class that why we tend to take most of the things at origin, because from origin to any point calculation of distance is very much easier. For our easiness and for our betterment, we take it at origin. We can take it even at some other point. Only thing is that we have to show the addition and subtraction little bit more. That's all. So taking capital Q to be positive, our charges are positive in nature. We wish to determine the potential at any point P with position vector R from the origin. We wish to define it at this point, okay. We must calculate work done in bringing a unit positive test charge from infinity to point P. How much work is done from bringing it from the infinity to point P? Because we are providing F external over here. This F external will give us W as F external into the displacement. For Q to be greater than 0, we have already defined it. The capital Q is positive. Again we are telling that Q is greater than 0. Work done against repulsive forces of the test charge is positive. Work done is independent of path. So any path it can travel, straight or any other path, but the work done for all the given 1, 2, 3 paths will be same. At some intermediate point P dash on the path, electrostatic force on the unit positive charge is given by its unit positive charge. So our small q will turn out to be 1. Force will be given as Q into 1 divided by 4 pi epsilon naught into R square into R cap, where R cap is unit vector along OP dash, unit vector for the given distance. Work done against this force from R dash to R dash del R dash is W equals to minus of Q divided by 4 pi epsilon naught R dash square into del R dash. So I'll explain this step as it looks little complicated to understand for one. See, what we basically are doing is we are force is defined as work is defined as force into the distance or the displacement. We have defined the force. Okay, now at this particular point, from I'll extend it from this point P dash to this point, some unknown point. The distance is R dash, del R dash, the small distance. Okay, so the work done to bring the charge from this point to this point is del W, the small work done, small work done. Okay, and it is given by charge, because this charge is producing the electric field. So charge by 4 pi epsilon naught into R square into the del R cap. So we have taken here del R cap because this del R cap will give us direction along del R cap. In other words, we can write it as force into displacement also. The same thing will come into the displacement of del R, Okay, the same definition of force can also be utilized over here. So the negative sign which appears over here is because Here del W will tend out to be positive. That's why this charge, this distance from the origin, if we look, is giving us a negative value. This distance del R dash will be negative. So once we introduce negative over here, these negative signs will cancel out to give us del W as positive. Now the total work done. Previously we have defined del W. Now the total work done W by the external force is obtained by integrating above equation from infinity to R. See, our charge previously, test charge previously was at infinity, and now we need to bring it to the position R. So we will integrate it from infinity to R. W equals to minus of infinity to R into Q by 4 pi epsilon naught into R dash square into dr. We are integrating it over distance. We are integrating it over distance or position. Okay? Now this Q 4 pi epsilon naught all are constants. So taking it out, and only this R square will be the one which will get integrated. So the integrated value we will get Q by 4 pi epsilon naught into R, 1 by R square into dr will be integrated as R minus 2 plus 1 divided by minus 2 plus 1. So we will get it as R minus 1 by minus 1. It will be minus R 1 by minus 1 by R, minus 1 by R. That is how it is integrated. I'll write above with a red ink so that it will be clear. Integration formula for the powers. Integration formula. X to the power n is given as xn minus 1. Wait. It is given as n minus 1 into x to the power s minus 1. Whereas these differentiation formulas are given in a different way. So that's how it's been integrated, and at the end we get a sum as Q by 4 pi epsilon naught into R. Here our work done is positive, we have seen, and this work done is having a relation with 1 by R, not with 1 by R square as in the case of energy and in the case of force. Okay, thus by definition, potential at P due to charge Q is given by V of R equals to Q by 4 pi epsilon naught into R. Work done equals to the potential carried by the system. Work done equals to potential carried by the system. So this equation is quite important. You should know. Now above equation is true for any sign of Q. Q can be positive, negative or anything. Though we consider Q positive in the above derivation, here we have taken as positive, but it does not matter. We can take a negative value of Q also. If Q is smaller than 0, then V will also be smaller than 0. That is, if Q is negative, our potential will also be negative. Work done, that is by external forces per unit positive test charge in bringing it from infinity to the point, is negative. This is equivalent of saying that the work done by electrostatic forces in bringing the unit positive charge from infinity to the point P is positive. Force on the unit positive test charge is attractive electrostatic force, and the displacement from infinity to P are in the same direction. Above equation is consistent with choices that potential energy at infinity is 0. So at infinity what we are defining is that our V equals to 0, At this particular condition, we are able to derive a relation at potential at R equals to Q upon 4 pi epsilon naught into R. Okay. So this is our graph over here. This is our graph over here. What does this graph signifies is that we are making a graph of electric field or electric voltage with respect to the distance. What is the formula for our electric field? I'll write on the right corner with the purple ink. Electric field is given as K into Q by R square. Here value of K is 1 upon 4 pi epsilon naught. Okay. So KQ by R square. E is proportional to 1 by R square. But this is true for E and this is true for the voltage. See, E is proportional to 1 by R square, whereas voltage is proportional to 1 by R. We have drawn a graph. V on the starting is like when the distance is less, it is very much. Then as the distance is increasing, it is slowly coming near to the lesser value. It is decreasing. But electric field which is more than potential at a given same distance, it is more. But as we are increasing the distance, electric field is decreasing more than the potential. E is decreasing more. Why? Because E is in relation with R square, inverse of like 1 by R square, whereas our voltage is in relation with 1 by R. If the distance is reduced by 1 centimeter, then the effect on the electric field will be 1 into 1 centimeter. If it is by 10, it will be 10 into 10, that is 10,000 times. E will be reduced, if R is reduced by 10, then E will be reduced by 10 into 10, that is 100 times. Whereas if R is reduced by 10, what will happen to voltage? Voltage will be reduced by 10 times. See, electric field is given by K into Q upon R square, whereas electric potential is given by K into Q upon R. Here Q is same as capital Q, only for like we always write small q, that's why I have written over here. And then potential and electric field. So that's how E is proportional to 1 by R square and V is proportional to 1 by R. This is the difference between them. This graph plays a very important role in understanding the concept, and with respect to the entrance examination, they usually ask you which is exponentially decreasing and which is decreasing with respect to R square, which is decreasing with respect to R. So one should know what will be the graph structure. When it is exponential, linear, constant, varying with R square, R cube, R, or 1 by R square, 1 by R cube, 1 by R, something like that. Okay. So whenever you read a concept and if there is a graph, always try to understand it with the relation of the coordinates which are placed over here, which are placed on the x-axis and y-axis. So what we have read in today's class, we have understood potential, that is potential that is generated due to a point charge which was on infinity and was brought by F external to position R. So how is the potential defined? Potential is defined at the position R as K into Q upon R, where W is the work done, which is also given by the same relation KQ upon R. So work done by this work done on that system and the stored potential have the same value, they are equivalent. So that's all for today's class. We'll come with a new concept in the next class. Okay, so have a good day. Bye bye.